Alkenes are a homologous series of hydrocarbons that has a double bond between a pair of carbon atoms and has a general formula CnH2n with N starting from 2. And they are called unsaturated hydrocarbons because they have a carbon-carbon double bond. And this functional group, the carbon-carbon double bond, is responsible for some of the unique reactions that are possible only by unsaturated hydrocarbons, and we'll see that here. But first, the basic reaction. Combustion. Being a hydrocarbon that is made up of only hydrogen and carbon atoms, the alkenes will burn in excess oxygen to form carbon dioxide and water. Consider the first member of the series C2H4 called ethene, and the 10th member of the alkene series C10H20 called decene. In the presence of excess oxygen, they undergo complete combustion to form carbon dioxide and water only. Every carbon atom from the hydrocarbon is burned in excess oxygen, meaning enough oxygen to get oxidized, and it's obvious that higher the carbon number, that is the number of carbon atoms in the hydrocarbon molecule, more oxygen needed for complete combustion. However, with limited oxygen, it undergoes incomplete combustion. Take decene for an example. It forms a range of products such as carbon dioxide, water, carbon monoxide, and leaves behind carbon, that is soot, depending on the amount of oxygen available. Carbon monoxide is a known pollutant which is harmful to living organisms. Comparing the combustion of small alkenes such as ethene and larger alkenes such as decene, the larger ones tend to produce carbon monoxide and soot, that is, undergo incomplete combustion due to more number of carbon atoms per molecule, that is, a larger molecule size. Comparing the combustion of alkanes and alkenes, the alkenes tend to produce carbon monoxide and soot, that is, undergo incomplete combustion due to the stronger carbon-carbon double bond. The second reaction type is called addition reaction. This is where the carbon-carbon double bond shows its unique properties. Alkenes are unsaturated hydrocarbons, which means it could be made to become saturated. The carbon-carbon double bond is obviously two bonds, and one of the bond can be broken, and another atom or group of atoms can be made to bind with those carbon atoms that had lost one of the double bonds. Being added into the alkene, such reactions are called addition reactions. In such reactions, the alkene loses its double bond to become a single bond, therefore becomes saturated. So, what can be added? The first addition reaction will be with hydrogen gas and is called hydrogenation, which is basically addition of hydrogen. Hydrogen is diatomic, that is 2 atoms per molecule. Consider the 2 carbon atom alkene, which is the first member of the group called ethene, and in this reaction one of the double bond between the carbon atoms break and the hydrogen-hydrogen bond from the hydrogen gas breaks. One of the hydrogen binds with this carbon atom while the other hydrogen atom binds with the other carbon atom. The hydrogen is added into the alkene molecule at the carbon atoms that had lost a bond, thus addition reaction. In this reaction, the alkene loses one of the bonds from the double bond, the other reactant gets added into the carbon chain and satisfying the requirement that carbon requires 4 bonds while hydrogen here requires 1 bond to be stable. The product formed has single bonds between the carbon atoms, and in this case of adding hydrogen, the 2-atom alkene ethene becomes a 2-atom alkane ethane. Basically, when hydrogen is added to an alkane is formed. Similarly with propene, the next alkene in the series with 3 carbon atoms has one of its double bond broken, the hydrogen atoms gets added into the carbon chain and it forms propane, which is an alkane. The next addition reaction is with water, H2O, where the H2O is added into the carbon chain and it is called hydrolysis. In the reaction between ethane and water, once again, one of the double bond breaks, and for H2O, one of the 2 HO bonds break, resulting in a H and an OH. The hydrogen binds with one of the carbon atoms that had lost a bond, and the OH binds with the other carbon atom to form ethanol, which is a member of the alcohol series. Basically, when water is made to react with an alkene, an alcohol is formed. Similarly with propene, the next alkene in the series with 3 carbon atoms has one of its double bond broken, the water H2O breaks to H and OH, the hydrogen atom and the OH gets added into the carbon chain and it forms the 3 carbon atom alcohol called the propanol. The next addition reaction is with the group 7 elements, halogens, and is called halogenation. Consider the reaction between ethene and chlorine, a group 7 element, a halogen. Chlorine is a greenish yellow gas at RTP and is diatomic, that is, it has 2 carbon atoms per molecule. In this reaction, one of the double bond breaks, and for chlorine, the chlorine-chlorine bond breaks, and both chlorine atoms binds with the carbon atoms that had lost one of the double bonds to form dichloroethane. Di means 2, chloro indicates chlorine being attached, and ethane because it's a 2 carbon atom hydrocarbon with no double bonds, therefore saturated. Consider the reaction between ethene and bromine, a reddish-brown gas and diatomic, that it has 2 atoms per molecule. And just like the case of chlorine, the bromine atoms gets added into the ethene to form dibromoethane, meaning 2 bromine atoms attached to a 2 carbon atom hydrocarbon ethane chain. The mechanism is similar in the case of propene and the halogens. Just take note which 2 carbon atoms have and had the double bond. The reaction between an alkene or any unsaturated organic compound and bromine is of much interest because bromine is a reddish-brown liquid, and when it participates in addition reactions such as these, the bromine is added into the organic compound and is used up and the reddish-brown color disappears. The bromine decolorization test is used to identify unsaturated compounds because of the very quick and distinctive color change from reddish-brown to colorless. The next addition reaction is polymerization. So far, we have seen hydrogen being added to alkenes, water being added to alkenes, halogens being added to alkenes, and now, is it possible for alkenes being added to alkenes? Yes, and that's polymerization, where the alkene molecules add themselves. Consider 5 of many ethene molecules. One of the double bonds in each of the alkene molecules gets broken, and being able to undergo addition reaction, they add each other at the carbon atoms that had lost one of the bonds. In this way, thousands of such molecules add themselves to form a giant structure called a polymer, thus polymerization. Each of the original molecules, which in this case is that of ethene, is called a monomer, and they add themselves to form a polymer called polyethene. Such giant molecules are simply represented as a repeating unit with n representing a very large number. The repeating unit is the monomer with one of the bond in the double bonds broken, and these two lines indicate that they are bonded to the other repeating unit on the right and one on the left, thus becoming the formula for the giant structure called the polymer. Consider 5 of many propene molecules drawn here in such a way that the double bond is clearly visible. One of the double bonds in each of the propene molecules gets broken, and being able to undergo addition reaction, they add each other at the carbon atoms that had lost one of the bonds. In this way, thousands of propene molecules add themselves to form polymer called polypropene. Each of the original molecules, which in this case is that of propene, is called a monomer, and they add themselves to form a polymer called polypropene. The giant molecule is simply represented as a repeating unit with n representing a very large number. Once again, the repeating unit is the monomer with one of the bond in the double bonds broken, and these two lines indicate that they are bonded to the adjacent molecules.